Welcome back to the deep dive. This is where we give you that shortcut, that deep understanding of the tech that's reshaping our world. And today, well, we're diving into AI engineering. If you're trying to get your head around the AI revolution, maybe you're a PM, an architect, or you just want to sound like you know what's going on, you really need to grasp the fundamentals.
That's exactly right. Our mission today is to break down 10 really foundational ideas, the papers and concepts that are basically the pillars holding up modern AI engineering. These aren't just like history lessons. They're the actual building blocks engineers are using right now to deploy large language models.
Yeah, we want to cut through the noise and give you that solid foundation. Useful for system design, definitely helpful for those tricky interview questions, and just, well, essential for understanding how fast this field is moving. Our sources cover the whole stack, from core architecture to scaling methods to making these things efficient and, safe to use.
And it all circles back to this kind of interesting question. Neural networks, the basic idea, they've been around since the 40s, right?
Yeah.
And used for decades. So why? Why did this huge LLM explosion only really kick off in the last, say, 5 to 7 years?
It feels like it needed a specific sequence of things to happen, like dominoes falling.
Exactly. You needed the right kind of architecture first, one that could actually handle getting bigger and bigger.
Well,
Then the discovery that just making it massive actually unlocked completely new abilities.
right.
And then all the engineering work to make that massive scale actually affordable and controllable.
So our timeline today really starts at that tipping point, doesn't it? Around 2017, when things just broke wide open. Okay, let's kick off with what pretty much all our sources agree is the absolute game changer, architecturally speaking. The 2017 paper, Attention is All You Need.
Ah, yes, the transformer paper. Its impact is, well, it's hard to overstate. Before this, the go-to models for sequential stuff like text were mainly recurrent neural networks, RNNs, and maybe some convolutional neural networks, CNNs, were adapted too, but RNNs were the main thing.
And what was the big problem with those older models? Like, from an engineering perspective, especially when we started getting all this powerful hardware like GPUs.
The killer limitation was sequential processing. Imagine an RNN reading a book. It has to read word 1, figure out its internal state, then read word 2 based on word 1 state, and so on, step by step.
Right, so it's like a chain reaction. Step 5 totally depends on what happened in step 4. You can't just do steps 1 to 10 all at once.
Precisely. And that led to, well, at least 3 major headaches that were holding back the revolution. First, training was incredibly slow.
Yeah.
You couldn't efficiently spread the work across lots of GPUs, which were becoming available then.
Okay, slow training.
Yeah.
What else?
Second, they really struggled with understanding context over long distances in the text, long-range dependencies. By the time an RNN got to the end of a paragraph, it might have completely forgotten what the start was about.
And there's a technical reason for that, forgetting, right?
Yeah.
Something our listeners should probably grasp.
Yeah, it boils down to something called the maximum path length. If you want to connect 2 words that are, say, 100 steps apart in an RNN, the information has to squeeze through 100 sequential calculations. The longer the text, the harder it was to keep that connection alive.
Got it. So the transformer arrives with this self-attention mechanism. How did that directly attack this path length problem?
Instead of that step-by-step process, self-attention lets the model look at every word in the sentence or document and figure out how relevant it is to every other word, all at the same time. It builds this kind of relationship map across the whole input in one shot.
Whoa. So it basically short circuits that long chain. The path length goes from being, proportional to the length of the text? ON, I think?
Yep, ON.
Down to just constant time, like O1.
That's the core technical leap. Making that path length constant did 2 revolutionary things. First, the model suddenly got way better at handling long-range context. A word 500 places away is just as easy to connect to as a word 5 places away.
Okay, better context handling.
And second, maybe even more important for the engineers, it enabled massive parallelization.
Ah, there it is. Because you can process all the words simultaneously, you could finally throw those huge GPU clusters at the training problem. Training times plummeted, costs dropped. It just changed the whole economic picture of building really big models.
Yeah, the sources are unanimous on this. The transformer architecture made scale feasible, even desirable. And pretty much every modern LLM you hear about, BERT, GPT, T5, you name it, they all stem from this basic design.
Okay, so the architecture is there. It allows for scale. The next big question researchers asked was, well, what happens if we just push that scale, like really, really push it? Which brings us to 2020 and the GPT-3 paper. Language models are few shot learners.
Right. And this one wasn't really about a new architecture. It was more of a stunning, almost accidental discovery about what happens when you make a transformer really, really big. Specifically, this new ability emerged called in-context learning.
And in this concept, in context learning, this is maybe the most practical thing for our listeners to get because it fundamentally changed how AI engineers worked almost overnight. Before GPT-3, if you wanted, say, a model to sort customer emails, you'd need thousands of examples, you'd fine-tune it, deploy it, a whole
Yeah.
process.
Exactly. GPT-3 demonstrated that you could take one giant general model and just by crafting the input prompt, carefully giving it instructions, maybe showing it a pattern, you could get it to do complex new tasks without changing the model's weights at all. That's in-context learning.
Okay, let's break down the prompting types they use to show this. The simplest one first.
That's zero-shot learning. It's purely instruction-based.
Yeah.
You just tell the model, translate this sentence from English to French, give it the sentence, and that's it. No examples. It has to rely entirely on what it learned during its initial massive training.
Okay, just instructions. Then there's one shot.
One shot gives it a single, clear example to steer it. So if you wanted names formatted a certain way, you might say, goal, format as last, first M example, input, Jane R. Doe, output, Doe, Jane R. Now format this. And then you give the new name.
Ah, okay. Just one hint to clarify the pattern. And the most powerful version for tricky stuff.
That's few-shot learning. Here you provide maybe 3, 4, 5 well-chosen examples right there in the prompt. This helps establish a more complex pattern or a specific tone you want or a tricky output format. The model kind of figures out the underlying rule from those examples within the context of that single request. It's like temporary dynamic learning.
Wow. And the big impact here, as you said, was the shift away from needing a dedicated, fine-tuned model for every little task, which used to involve a lot of what they called feature engineering,
Right.
to focusing instead on prompt engineering. Suddenly, this one massive model could power hundreds of different applications just by changing the input text.
It completely reframed how you build AI systems. It proved that scale, combined with that transformer architecture, really did lead to a kind of generalized intelligence, which meant the next big problem wasn't just make it bigger, it was make it behave.
That leads perfectly into the next phase.
Yeah.
Okay, so now we have these incredibly powerful, scaled-up models, but anyone who played with the early raw versions knows they were also kind of wild. Unpredictable, sometimes unhelpful, sometimes they just make stuff up, sometimes they'd even generate harmful content. They weren't exactly user-friendly.
Yeah, scale unlocks raw power, but it doesn't automatically make a model helpful or safe. It doesn't give it alignment. And that brings us to a really crucial engineering step, formalized around 2022, detailed in the Instruct GPT paper. This paper popularized a technique called RLHF reinforcement learning from human feedback.
The goal seems pretty clear. Take that powerful but chaotic base model and train it to be consistently helpful, honest, and harmless. So walk us through the main steps of RLHF. This process is basically behind the feel of every major chatbot today, right?
Pretty much. Step 1 usually starts with something called supervised fine-tuning, or SFT. Basically, researchers collect a data set of prompts paired with high-quality, human-written answers that show the model exactly how it should behave. Answers that are safe, helpful, follow instructions precisely. The base model is then fine-tuned on this data set. It's like giving it an initial good behavior manual.
Okay, so step 1 is like showing it the ropes, teaching by example. What's step 2? This is where the human judgment comes in more directly, I think.
Exactly. Step 2 is building the reward model. This is usually a separate, smaller model. Its only job is to learn to predict human preferences. How it works is, you take the base model, have it generate several different answers to the same prompt. Then you show these answers to human reviewers, and they rank them from best to worst. The reward model is trained on thousands of these human rankings. Its goal is to output a score, just a number, indicating how much a human would likely prefer a given answer.
Ah, that's clever. So the reward model becomes this sort of automated judge of goodness, capturing all those subtle things. Humans like politeness, clarity, actually answering the question, things that are hard to just write down as rules.
Precisely. It learns the nuances. And that reward model is the key input for step 3, policy adjustment. This is where the reinforcement learning part really happens. The score from the reward model acts as the reward signal. The main LLM's policy, essentially how it decides the next word to generate, is then tweaked using RL algorithms to try and maximize the score it gets from the reward model.
Okay, and that tweaking usually involves algorithms like PPO, proximal policy optimization. The idea being to make the model chase that reward score, but without drastically changing its core knowledge or forgetting everything it learned during pre-training.
Yes, exactly that. You want it to get better according to human preferences, but not become stupid in the process. The whole point of this RL loop is to generate answers that the reward model thinks humans will prefer above all others.
And the really big finding from Instruct-GPT, which was kind of surprising at the time, was that this alignment process was actually more important than just raw size.
Absolutely. The researchers found that a smaller model, like their 1.3 billion parameter Instruct-GPT, when properly aligned using RLHF, was significantly preferred by human testers over a much, much larger, unaligned 175 billion parameter model. It proved that for users, feeling like the model understands and follows instructions is often more valuable than just having more raw knowledge. Control trumps scale for usability.
And the sources also mentioned that this field is moving fast. RLHF works, but it's complex, computationally heavy. People are now looking at things like DPO, direct preference optimization.
Yeah, DPO is seen as a more recent, perhaps more efficient approach. Instead of needing that separate RL training loop driven by the reward model scores, DPO tries to learn the optimal policy directly from the human preference data itself. It aims to achieve the same alignment goal, but in a potentially cleaner, more stable, and maybe less computationally expensive way. It's about streamlining that whole alignment pipeline.
Okay, so we've got the architecture transformer, the scale that brings intelligence, GPT-3, and the alignment that makes them usable, RLHF. But let's be real, these things are still gigantic. They use tons of memory, cost a fortune to run, and modifying them for specific tasks is a major headache. So now we need to talk about the breakthroughs that made LLMs actually practical and affordable to deploy and adapt.
Absolutely critical. And a great place to start is making adaptation cheaper. That was revolutionized by the 2021 LoRA paper Low Rank Adaptation. Think about it. Fully fine-tuning a model with, say, 70 billion parameters means updating all 70 billion weights. That takes huge amounts of compute time, energy, and very expensive hardware with tons of GPU memory. It was just out of reach for most people.
Right. So LoRA came along with a really clever workaround. What's the basic idea behind it? How does it avoid rewriting the whole model?
It's based on this idea, sometimes called the intrinsic dimension hypothesis. It suggests that even though the model has billions of weights, the actual change needed to make it good at a new specific task might live in a much smaller, lower dimensional space.
Okay, so you don't need to rewire the entire brain, maybe just tweak a few key connections or add a small specialized circuit?
Kind of like that, yeah. LoRa inserts pairs of very small matrices. These are the low-rank adapters, next to the huge existing weight matrices in the transformer layers. And here's the kicker. The original massive pre-trained weights are frozen. They don't get updated at all during fine-tuning. You only train these tiny little adapter matrices. They learn to just subtly nudge the outputs of the big matrices in the right direction for the new task.
So if the base model has billions of parameters, how much smaller are we talking for these trainable adapters? What kind of reduction do the sources mention?
It's pretty staggering. The papers show reductions of 10,000 times fewer trainable parameters compared to updating everything. And because you're training so much less, the GPU memory needed during training also drops significantly, often by about 3 times or even more, depending on the setup.
Wow, 10,000 times fewer parameters to train. That's what really opened the door, right? It meant you could potentially fine-tune these huge models on just a single decent GPU instead of needing a whole cluster. Made specialization much more accessible.
Exactly, it democratized fine-tuning. And that idea of efficiency leads nicely into another concept for managing scale, mixture of experts, or MOE, popularized by papers like Switch Transformers. This is about scaling up capacity without scaling up the cost proportionally.
Okay, MOE, it's about being selective, right? Can you explain the difference between a standard dense model and one of these sparse MOE models?
Sure. In a standard dense model, let's say it has 100 billion parameters. Every single one of those 100 billion parameters is involved in the calculation for every single word or token that goes through it. Very computationally heavy. And MOE model is different, and it still might have a lot of parameters in total, maybe even a trillion. But these parameters are divided up among many smaller, spiralized expert networks.
Okay, lots of little specialists instead of one giant generalist. How does that save compute?
Because for each token coming in, there's a small router network that quickly decides which one or maybe two of these experts are the most relevant for processing that specific token. Then, only the selected experts run their calculations. The rest stay dormant. So you might have a trillion parameters of knowledge capacity stored, but for any given token, you're only paying the computational cost equivalent to running, say, a 100 billion parameter dense model.
Ah, I see. So you get the benefit of that huge capacity, that stored knowledge, but the actual cost per token at inference time is much lower. Sounds like a win-win.
Well, in theory, it's fantastic as how companies build models like Google's Gemini or some versions of Llama that have enormous parameter counts without inference being impossibly slow or expensive.
Yeah.
But the sources also flag a pretty big engineering challenge here.
Wait.
Running these sparse MOE models in production is complicated. You've got all these different experts, potentially hundreds of them. You need to make sure they're all loaded, balance the traffic so some experts don't become bottlenecks, manage potentially heterogeneous hardware, keep latency low. It's a significant operational burden.
Right. So the infrastructure complexity might eat up the computational savings for some teams.
Exactly. We hear that for many, especially enterprise teams, without massive dedicated infrastructure groups, sticking with a well-optimized, medium-sized, dense model plus good tooling might actually be simpler and more cost-effective overall than wrestling with MOE complexity.
That's a really practical point. The total cost includes the human engineering effort.
Absolutely. Okay, let's shift gears slightly to compressing models, which is crucial for getting AI onto devices people actually use. This takes us back to 2019 and the Distilbert paper, which focused on knowledge distillation.
Right. The goal here is pretty straightforward. Make the model smaller and faster, but try to keep most of its smarts.
Yep. The method uses a kind of teacher-student setup. You take your big, powerful, well-trained teacher model. Then you train a much smaller student model, maybe with 30–40% fewer layers or parameters, not just to predict the right answer, but to mimic the output probabilities of the teacher model during pre-training.
So the student isn't just learning the answers, it's learning how the teacher thinks or arrives at those answers, trying to capture the nuances.
Exactly. It forces the smaller model to learn a more efficient representation of the knowledge. And the results were impressive. Distilbert, for example, ended up with 40% fewer parameters than the original BERT model, was 60% faster at inference time,
Wow.
and still retained about 97% of BERT's performance on language understanding tasks.
And why is that kind of speed up and size reduction so vital for real-world use?
Edge devices. Everything that isn't a giant server in a data center. Think about running sophisticated AI on your phone or in a car or on equipment in a factory. These devices have tight limits on memory, they need answers fast, low latency, and sometimes they can't rely on a constant internet connection or they need to keep data local for privacy. Distillation is a key enabler for getting powerful AI off the cloud and onto these devices.
Okay, makes sense. Which brings us to our last big efficiency technique, maybe the most technical one, shrinking the memory footprint even further using quantization, specifically the breakthrough detailed in the 2022 LLM.int8 paper.
Right. Quantization at its core is about using fewer bits to store numbers. Instead of using, say, 32-bit floating point numbers, FP32, for all the models, weights, and activations, you try to use something smaller, like 8-bit integers, int8. Doing that can potentially cut the memory needed for those weights by 4x, and it often makes the math operations faster, too.
Okay, seems like a basic optimization. If it saves so much memory, why didn't it just work out of the box for these huge LLMs? Why was it a breakthrough in 2022?
Because when you scaled transformers up to billions of parameters, something weird happened that broke naive quantization. The LLM-based researchers pinpointed the problem: outlier features.
Outliers. What are those exactly in this context?
They found that within the massive matrices, particularly in the feed-forward layers, there were specific dimensions or channels whose activation values would sometimes become enormously larger than all the other values around them, like orders of magnitude larger. When you tried to naively quantize everything down to int8, these huge outlier values got squashed into the small 8-bit range, losing a massive amount of precision. It was like throwing away critical information, and it caused the model's performance to just collapse.
Like trying to measure the height of a skyscraper and the height of an ant with the same ruler marked only in kilometers. You lose all the detail for the small stuff, or you can't represent the big stuff accurately.
Exactly. So the LM.int8 breakthrough was realizing this and proposing mixed precision quantization. They don't quantize everything uniformly to int8. Instead, their method dynamically detects these problematic outlier features during inference and keeps just those specific outlier values in a higher precision format, like 16-bit floating point, FP16 or BF16, while quantizing the vast majority of the other normal values down to int8.
That's clever engineering. Find the critical bits that break things, protect them, and compress everything else aggressively.
Precisely. And the impact was huge. It roughly halved the GPU memory needed just to load the model weights and activations for inference. This suddenly made it possible to run really large models,
Hmm.
like 65 billion parameters or more on a single high-end GPU, whereas before you would have needed multiple GPUs, a whole cluster sometimes.
So it drastically lowered the barrier to entry for using large models, cut down serving costs, and made prototyping much faster for smaller teams. A huge practical win. Okay, we've tackled architecture, scale, alignment, and efficiency. We've built this powerful, optimized engine, but an LLM sitting alone is still kind of useless in the real world. Now we need to talk about how these models connect to external data, how they interact with other systems, and how they can actually do things, the integration piece.
Yeah, this is crucial. As we touched on, LLMs have a knowledge cutoff day. They only know what they were trained on, and they have this tendency to, well, hallucinate, make stuff up confidently. The first big breakthrough to tackle both those problems head-on was Retrieval Augmented Generation, or RA, which really gained traction around 2020.
Or RG, it's basically like giving the LLM an external, up-to-date, verifiable brain extension, right?
What?
How does that process actually work?
It's usually a three-step flow. First, the user asks a question. Second, and this is the key part before the LLM even sees the question, a separate system, the retriever, searches a specific knowledge source. This could be a company's internal document database, a vector store of product manuals, or even the live web. The retriever finds documents or snippets that seem highly relevant to the user's query. Third, the system takes these retrieved pieces of text and bundles them together with the original question, feeding all of that into the LLM's context window. The prompt effectively becomes, based on these documents I just found, answer this question.
So you're grounding the LLM's answer in specific, hopefully reliable external information. This seems absolutely essential for any business use case, right? Where you need answers based on current company data, not just general knowledge from 2022.
Non-negotiable for most enterprise uses. And interestingly, the engineering focus often shifts here. Our sources suggest that the quality of your retrieval system, how good it is at finding the right documents, often matters more for the final answer quality than minor differences between various base LLM models.
So the engineering challenge moves upstream to the retrieval part. What kind of techniques make a difference there? It's not just simple keyword search, is it?
Oh, definitely not. It starts with how you prepare the documents called chunking. Just chopping documents into fixed-size pieces isn't great. Modern RAG uses smarter methods like recursive chunking that tries to keep semantic meaning together, or semantic chunking based on embedding similarity. Then there's the retrieval itself. Basic vector similarity search is a start, but more advanced systems use things like query rewriting. They might use a smaller, faster LLM to take the user's potentially vague question and rewrite it into several more precise, targeted search queries to hit the database with.
That makes sense. Refining the question before searching should lead to much better results being pulled back.
Exactly. And RAG is evolving fast. We're seeing multi-step ARIC pipelines where the LLM might retrieve some initial documents, realize it needs more info, formulate a follow-up query to itself, retrieve again, and then synthesize an answer from everything it found. This complexity demands better ways to evaluate ORI systems too, looking at metrics like faithfulness, meaning how well the answer sticks only to the retrieved facts, and groundedness, ensuring every claim made can be traced back to a specific source document. RA makes the LLM more of a processor and synthesizer, less of a know-it-all oracle.
Okay, so RA gives models access to data. The next logical step is letting them act on information to actually perform tasks. This brings us to LLM-based agents, which a big 2023 survey paper really helped define.
Right. Agents are systems designed to tackle complex, multi-step goals more autonomously. For listeners trying to get a handle on them, the survey offers a simple, useful framework. Think of an agent having three main parts: a brain, perception, and action.
Okay, let's break those down. The brain.
The brain is the LLM itself. Its job is the high-level thinking, understanding the goal, breaking it down into steps, reasoning about the current situation, maybe replanning if something goes wrong, and deciding what to do next.
That makes sense. Perception.
Perception is how the agent takes in information from its environment or its tools. It's the input stage. After it takes an action, it needs to perceive the result. Did the code it ran produce an error? What is the API it called return? What's in the document it just retrieved? It needs to make sense of that feedback.
Okay, brain plans, perception observes, and action.
Action is where the agent actually does something in the world, usually by using a predefined tool. This could be calling an external API, like booking a flight or checking inventory, running some code in a sandbox, writing to a file, searching the web. The agent performs the action, the result feeds back into perception, the brain analyzes it, and decides the next action, and this loop continues until the goal is achieved.
And the survey mentions different ways to set these up, right? Not just one agent doing everything.
Yeah, you can have a single agent working through a sequence of tool calls. Or you might have multi-agent systems where different agents specialize. Maybe one agent is good at planning, another is good at writing code, a third one critiques the code, they collaborate. You even see concepts of agents working alongside humans.
But getting these agents to work reliably, that sounds like another big engineering hurdle. What did the sources say is critical for building practical agents?
Two things come up constantly. Very clear tool schemas. The LLM needs to know exactly how to call each available tool, what parameters it takes, what format they should be in, what it returns. Usually this is defined using something structured like JSON schema or OpenAPI specs, no ambiguity allowed. And second, robust guardrails. Agents can potentially run for a long time, use a lot of resources, costing money, or even get stuck in loops. You need mechanisms to monitor them, enforce limits on steps or token usage, detect repetitive actions, and potentially have safety layers to prevent harmful or unintended consequences.
Yeah, you need ways to make sure they stop eventually and actually produce something useful and safe.
Absolutely. Verification and validation are key. Which brings us to the final piece of the puzzle. How do all these different components, the LLM, the RAG system, the agent framework, all the various tools and APIs and databases actually talk to each other without requiring engineers to write tons of custom glue code for every single connection? This is where the idea of a standardized protocol comes in, like the Model Context Protocol, or MCP, proposed by Anthropic in 2024.
Okay, MCP. What problem was so bad that it needed a whole new protocol?
It was basically integration chaos. Before something like MCP, if you wanted your agent system to talk to 5 different internal databases and use 10 external APIs, you were writing bespoke, brittle integration code for each one. You had to figure out how to format the API calls, how to parse the results, how to manage the context window as information flowed back and forth. It was a nightmare and didn't scale well at all. Every new tool was a major engineering effort.
So MCP tries to create a universal translator, a standard way for models and tools to communicate. How does it work?
The idea is you run MCP servers that act as standardized gateways to your tools and resources. These servers expose the tools, their capabilities, and even the current state of the prompt or conversation using a common, defined schema. Any client application that understands MCP, maybe your IDE as a specific agent runtime environment, even a chat interface, can then connect to these servers, automatically discover what tools are available, know how to call them correctly using the standard schema, and handle the streaming of results and context management in a consistent way.
Ah, so it abstracts away all that custom integration work.
Yeah.
The tool builder exposes it via MCP, and the agent builder consumes it via MCP, and they just work together.
That's the goal. It's a huge potential boost for developer productivity and making these complex AI systems more modular and interoperable. It's about plugging these powerful models into the existing ecosystem of software and data much more seamlessly. Hashtag, outro, final synthesis, and provocative thought.
Wow, okay. So we've really covered a lot of ground there, tracing the key steps that brought us to modern AI engineering through these 10 concepts. Let's just quickly recap that journey for everyone listening.
Sure. It really started with the core architecture, the transformer, which finally allowed for the parallel processing needed for massive scale. That scale, exemplified by GPT-3, then surprisingly unlocked new abilities like in-context learning.
Right. But raw scale was messy, so we needed alignment, which came through techniques like RLHF and now DPO, making models follow instructions and behave predictably.
Then came the wave of crucial efficiency engineering, making adaptation affordable with LoRA, scaling capacity smartly with MoE, shrinking models for deployment with distillation, and slashing memory usage with quantization like LLM.NT8.
And finally, we looked at making these optimized models actually useful in the real world, giving them access to current knowledge with RA, enabling them to take action autonomously with agents, and allowing seamless integration with everything else via standards like the Model Context Protocol, MCP.
Yeah, the big takeaway for you listening should be that building successful AI systems today isn't just about training the absolute biggest model possible. It's much more about the clever engineering involved in connecting, controlling, optimizing, and integrating these models using the principles from these 10 breakthroughs. These are really the fundamental techniques you need to understand for effective system design right now.
Definitely. And as we wrap up, we deliberately didn't dive deep into things like the specifics of hardware accelerators or the underlying scaling laws that predict model performance. We focused on the algorithmic and system-level innovations.
But thinking about that efficiency trend, look how quickly things like quantization and LoRA and sparse models have advanced, all aimed at reducing the compute needed for both training and inference. It leads to a really interesting question for you to think about after this. If almost all the cutting-edge research continues to focus so heavily on reducing the computational cost, on making these huge models runnable with less power and memory, what might model serving realistically look like in, say, just 3 years from now? Could we see today's frontier models running effectively, maybe even routinely, on standard laptops or even edge devices?
That's the big question, isn't it? How far can this push for efficiency take us? And how much will it truly democratize access to this incredibly powerful technology? Something to keep an eye on. Thanks for diving deep with us today. We'll catch you on the next one.